Good morning, guys. Happy St. Patrick's Day. Even though we're not in class, I thought I'd go ahead and still do our demos as if we were. So let's hope this works well. All right, this experiment is called Walking Rainbow. And the idea is we take the primary colors of red, yellow, and blue, and they are going to pull from one cup to the other using capillary action. So we'll add some red dye to the first beaker, blue to the third, yellow to the fifth, and red to the seventh. Now we can see that it's starting to pull up the paper towel already. I'm going to add some extra water to move it along. You can see the blue's pulling up already, as is the yellow. Now this one will take a couple of hours to run, so we'll come back. All right, this next one is Skittles Rainbow. So we have red, blue, and yellow Skittles in alternating patterns. And then I have a beaker of warm water that I'm going to pour into the center. And if it goes well, the sugar coating on the Skittles should start to dissolve. There you can start to see it leaching out. And they will start to mix our colors again. While that's going, we can check on our walking rainbow. We can see the red is pulling over and the yellow is pulling over. The yellow is actually moving quite a bit. And the blue's coming over. In fact, it started to seep through to the other side. And the red's having difficulty on this side. So back to our Skittles. You can see they're seeping together. Hopefully they start to mix and start to show us some of our secondary colors. Well, they were getting a bit of green coming through with the blue and the yellow. And this couple minutes later, we can see that they're really starting to move, and the colors are being combined. We're starting to get some purples between the blue and the red, and some greens between the yellow and the blue. Not seeing so much in the way of orange yet, but it may be just harder to tell with the yellow and the red. Alright, now a couple minutes later again, we have a lot of mixing of colors. In fact, it's starting to turn all brownish because we're going to that point where all the colors are being melded together. But we can see the purples and greens and oranges now. Alright, this next one is called Rainbow Paper. And you've got a big bowl of water and black cardstock and then clear nail polish. Now, the clear nail polish that I borrowed is quite old and quite thick, because really all you want to do is do a drop of clear nail polish on top of the water. Then you dip the black cardstock in and you pull the cardstock out. This nail polish is old enough and thick enough that it requires 2 hands to get it out of the bottle, and so you're not going to see that part of the action. I'll have to show you the after effects. See how well this works. Alright, while that one dries, I can show you one that I did earlier. And you can see the iridescence in it, that changing of colors. So this is due to thin film interference. And thin film interference is what causes the iridescence on mud puddles in a parking lot. It's the oil floating on top of the mud puddle, or when you blow up a balloon and you see the rainbow pattern, or not a balloon, a bubble. When you see a rainbow pattern in a bubble, that's thin film interference. And what's happening is that light is actually reflecting off the top of the film and the bottom of the film differently. And so to our eyes, it looks like a rainbow pattern. It's actually light being reflected off the top and the bottom layers of that film independently. All right, our last demo about rainbows is looking at refraction, which is a splitting of light. This is looking through a prism. Now, of course, I needed a bright sunny day to do this, and so I got a gray cloudy day because that's how my science demos go. But if you look closely in the prism, you can see the colors of the rainbow being split out. I'm going to try this with a flashlight here in a minute and see if we get better results. All right, not great, but using a flashlight and prism, if you look at the top right of the paper, you can kind of see the colors separate out as I move the flashlight back and forth. Now, with the flashlight, you can't use an LED. You have to use a traditional bulb. An LED, the wavelength is so controlled by the LED that actually cannot split it out because it's one wavelength of light that's going in. If I double up on my prisms, we can get a little bit better rainbow effect with this flashlight. So refraction happens because the speed of the light entering the prism changes because of the prism. And that change causes dispersion or separating of the wavelengths of light into its different colors. So now we can see, with two prisms, we can see the rainbow a little clearer. And you can see if I move the flashlight, how it changes the angles as it moves through the prism. Changes the rainbow as well. Alright, and our last attempt is using a glass prism that actually hangs in my kitchen window at home. When the sun shines through it, it creates rainbows sparkling through the whole room. So you can see with this prism, it's got all sorts of facets cut into it, different faces cut into it. Light going through it, we can see some of those little mini rainbows that come refracted out of the prism. All right, and the last thing we're going to look at is the science of the rainbow. So for our 7th grade, this is not new information. We looked at it when we looked at the electromagnetic spectrum, and that's what we're looking at here. This is all the different types of rays that are coming from the sun. So we have gamma rays starting at this end, going to X-rays, ultraviolet, which is UV. The tiny little band here is visible light. That's our white light. And then infrared, which is heat energy, and then radio waves and TV and FM and everything that our phones run off of is clear down here. Up at the top you can see that this is the wavelength. So these higher energy ones have a very short wavelength, and as we go across the spectrum it slows down and the waves get spread out much further. So the wavelength increases. Down here looking at the visible light, when we break out the spectrum of colors, we run to at about 380 nanometers on the violet side, clear up to 740 on the red side. And so our atmosphere does a good job of breaking these out. This is why we see a blue sky, it's because the light's being refracted. It's why we see a bright red sunset and sunrise, is because all the other colors are being scattered as that sunlight's going through so much of our atmosphere when it first rises and sets, and so all we see are the reds coming through. Alright, so this is about an hour after we started. You can see purple is starting to form with the red and blue come together. We got some definite green going on there, and some orange with the red and yellow.